Yo everybody, we're back on the 2018 AS Physics Unit 1 exam. Question 3 is about your Young's modulus and classification of solids. Question starts with describe a method to investigate the force extension properties of rubber. Okay, so sometimes it's a steel wire, but this one is the rubber one. Make sure you learn all the stuff. You should describe how the extension of the rubber is accurately measured. So a fabulous diagram there of a stand clamped onto a rubber band with some weights hanging from it and a ruler measuring the extension. Pretty crude, but that's all they're looking for. Ensure the stand is secured and stable. Place a ruler very close to the band, ensuring 0 millimeters on the ruler is in line with the base. Add weights incrementally and measure the extension each time. You might even want to do it a few times and calculate the mean. They like to hear that as well. Right, and the results form this hysteresis graph here, okay, that you should have learnt off by heart from your notes. And they're probably going to ask us why the gradient is shallower here than here. And we'll talk about spaghetti. Let's have a look. Right. Calculate the strain at point B. Of course, strain is extension divided by original length. So if I go to point B, I can see the extension is 6. The original length was 8. Sorry, I wasn't on camera. Point B, extension is 6. Original length 8. So that's 0.75. Notice there's no units because it's a length divided by a length. Now, even though those figures are in centimeters, it wouldn't matter, because even if I converted them to meters, 0.06 divided by 0.08 would still give me 0.75. But always be aware of your units. Determine the Young's modulus then, right? So Young's modulus E is stress divided by strain. We've just worked out the strain, so now we need to calculate the stress. Stress is force divided by area, and they've given us the cross-sectional area. They've given us it in centimeters squared, mind. Don't forget there is 100 times 100 square centimeters in a meter. So using this, I want to keep it all in my SI units, right? So I've put that times 10 to the minus 4, so it's in meters squared. I can use the 7 then in newtons, right? So the Young's modulus of the rubber in the region AB. And of course, if I go back to the graph from A to B, the force in newtons is 7 newtons, right? I've put my area into centimeters squared. I've done force divided by area to get that newtons per meter squared. My Young's modulus then is that value of stress divided by that value of strain. And I can put that final one then in pascals because all my units were in the right things, right? 1.87 times 10 to the 6 pascals. Don't forget, if you're doing this for a steel wire, right, you're looking for that power of 10 to be about 11, right? 6 for rubber, about 11 for a steel wire. And then finally, by referring to the molecular structure of rubber, explain why the gradient in the middle is less than at the end, right? So that's what I was referring to earlier. So here, of course, we need less force to produce the extension, hence the gradient is shallower, because we just are untangling that plate of spaghetti, don't say that though, untangling those long chain molecules. And once they are untangled, we then need a greater force for extension, hence the much steeper gradient, because we are then stretching or even breaking those long chain molecules. So that's something you just need to learn off by heart to get those 3 marks, which I'm sure you have done. A nice question on that topic this year. I hope you get one like it.